Hi, today I'm gonna present our final project for the optimal control course in our school. So we are the team 4 and we what the project consists is to create an control law following the optimal control techniques and apply this law in some system. So for the system, we chose an op-amp, an operational amplifier with a certain configuration, which is a double low-pass filter. Why is it double? Because, as we know, the configuration of a resistance and a capacitor in this way gives us a low-pass filter. But also we have instead of a resistor as a feedback, we have another capacitor. So this capacitor also works as a low-pass filter. So it turns out that this configuration is a double low-pass filter. Okay, and what we desire to control is the output voltage given certain input. And for the resistor and capacitor values, we chose these ones. This would be 50k ohms. For this would be 10k. This one 100k. This one would be 10 microfarads, and this one 50 nanofarads. And first, we need to obtain the mathematical model for this system, and before make designing the controller, because we need some values and some numbers of the mathematical model. So first is a simply mathematical outlook for an op amp. It's a generic standard guide for obtaining the output value in reference of the input value. So our output value, the double derivative of our output value would be this equation, and then we obtain the state space representation. So we are setting for our x1, that would be the output value, and our x2 would be the derivative of that value. And for the input, we're gonna take the input voltage, and that gives us the following state space model. And this is in its generic form. Later we are gonna substitute these parameters with their proper magnitudes. Okay, so then once we have our model in a state space representation, what we are gonna do is to confirm if this model is controllable, observable, and also to analyze the stability of the system. So for controllability, we need to obtain this matrix and to see if its range, if it is different from 0, and turns out it is. So we take the determinant of this matrix to see the range of it, and it does differ with 0. Okay, and for observability it is the same, but we take the conjugate of every value as is seen in this representation, and then we are gonna take the determinant to see the range, and turns out it is also different from 0. And for stability, we take another analysis, and we take the eigenvalues, and they are in the left side of the root locus plane, in the negative side. So it is a stable system with some natural frequency, and we see the root locus representation, and we see that we are in the negative axis. It is not uh, uh, kindly visually here because we have some high values, but as you see with the poles it is in -6, the two of them, and when they meet we have a gain of 0.5. Okay, and in open loop the system gives us the following response in the time domain. Okay, so and our gain is of -2. So now that we okay, so that's our system, that's the behavior of our system. So now we are gonna propose control control reference. What we're gonna propose what we want to control. So we want to control the output voltage of the op amp, and we want the voltage to reach a reference of 10 volts. Also to reduce the settle time, the steady state time. Okay. So what in what consists the optimal control techniques? Well, we have to propose a cost function. So this is our cost function equation in terms of the input value, the output value, and the state space and the states values. So this would be our state value or first state value, which is the output voltage, and this would be our input value or control value. And this number represents the penalization for each state. So this state has more penalization than the input value. And to the restriction for in these equations to tell it to reach 10 volts is here in this reference. So we are integrating the error instead of just the x value. So this gives us the following cost function, and now we are gonna develop the all the gains and the cost function law for this particular system with these particular restrictions. And so this would be our system in state space mode. This would be our cost function. So these two equations derives the following matrices. So this would be our A matrix from our state space system, the B matrix, and the cost function doesn't have the H matrix. Its value is 0, and the Q matrix penalization only is taking in consideration the x1 state. So we are only work with that state and ignore the second state. And our R matrix is just a scalar value, and it is represented as 1 over 15. And our reference matrix is just the 10 volts reference for the first value, and we don't have a reference for the derivative of the output value, which is the x2. So to design our LQR controller, we have to use the Riccati equation to take the k gains, and this is the general form of the Riccati equation, and we are gonna substitute and solve this equation for the derivative of the x values, and turns out that we have the following system in the following differential equation system, and we are gonna solve this differential equation system to obtain the proper k values. And now we are gonna take the S matrix for the reference value and do the same steps to solve this general form, and turns out that we have as the following as values in a differential equations. So also we have to solve for these two differential equations. And the optimal control law is in its general form is the following. So we take the inverse of R, the transpose of B, we multiply the K matrix, and that multiplied with the X values, the states values, and then we are gonna subtract the same inverted R value times the B transposed times the S matrix, the reference matrix, and we solve for U and gives us the following control law. Turns out that it is in its general form for our system, and now we should solve for the K and S values. So to simplify the problem, since we are only taking in consideration the a pretty long time from the dynamics of the system, so we are gonna assume that our final time is that converges to infinity, and also we know that our H matrix is 0, so that gives us the following simplification. We say that that the differential equation system we can set to 0 for K and for S, so gives us the following equation system, and it becomes in an algebraic problem. So at this point we are gonna solve for every value, and it gives us the following gains, and substituting in our control law gives us the following representation with numbers. So we are gonna use some some scripts in Scilab to simulate our mathematical approach of every dynamic, and we are using this code, this script, that this script is based on the one of the one provided by the professor. So we took the scripts that the professor gave us, and we modified this script to obtain a general form for every 2 by 2 system. So basically we only with this code we only have to worry about modifying the state space system and to modify the cost function for them in terms of the matrix of the matrices, and the code below is just to is just it we don't need to modify anymore because it's in its general form. So here we are taking the K and S matrices and solve them. So and we are gonna save those dynamics here in these two matrices in the K, capital K and capital S. Then we simulate the plant model with its proper controller here, and we are gonna feed the system with this input. Then we are gonna obtain the graph for the cost function and the input function in function of time. Then we are gonna plot the first the dynamics of the K and S gains. Then in the second graph we're gonna graphic the dynamics of the voltage and the derivative of the same voltage, and also we are gonna display the reference value. For the third graph we are gonna graph control law, the optimal control law. And for the last graph, we are gonna display the cost function over time. So here, just let me modify the this code to what we have so far in in our in our presentation. So you just have to click play and it will simulate all the graphs. It's taking a little time, maybe because it's too much information to process. And also I forgot to modify the H and Q matrix values. So let me modify those values according to this cost function. Can't find the cost function. Okay, here it is. So for Q we have 0.04 and for R we have 0.02. Okay, so let me close this simulation and just reopen Zylab. But basically, you just have to click play in that script and give, and it will display the following graphs. Okay, let me let me modify this H value was 0.04 and this one was it 0.02. Let me corroborate that. Yeah. Okay. So and let me modify the resolution. Okay, it is giving me some errors. 3 and okay, here I have some problems. So I made a mistake. So here it is 0.04 and here it is 0.02. Play. Still having issues. Okay, let's forget about this code. I think I modified something that I should not. And well, basically, it will give us the following graphs. And so here it is the Riccati's matrices and the reference matrix, the K matrix and the ACE matrix. And we can see that it reaches some point, some constant values, and the system will take that will make the controller for with those values, and it will perform the following dynamic. And if we zoom in the first state the first state value, the blue one, we see that it gets stuck at 8.88 instead of reaching the reference. So we have to modify our cost function in order to meet the 10 volts. And here it is the input dynamic and also the cost function over time. So I don't know why here I have some errors. I think I need to reset my code. But let's keep talking about the problem. So now we are gonna readjust our cost function. So the first method, which was proposed in the literature, in the documents provided by the professor, they talk about this method. So we did it, but still doesn't give us a proper control law. So we made a second iteration. Um, this method is just by proof and error. So just let me reset the code and open it again. Okay, just let me confirm it works. Okay, now it is working, but not with the proper value. So let me modify the parameters. So for h we have 0, for q we said it was 0.04, and for r it was 0.02, right? So let me play it again, and now we have the following dynamics. It is in the presentation. Okay, so this is the cost function. Then we have the input control law. So here it is shortened in 0. In 80 milliseconds, and here it is at 300 milliseconds. So that's why it seems like pretty reduced, pretty quick, but it's actually the same dynamic. So later we have the state dynamics. So let me display that. So here is the state dynamics, and if we zoom in the first state, we see that it doesn't reach the 10 volts. It stays at, as we said, 8.88. So we need to modify the cost function in order to meet the 10 volts reference, and we said that this approach didn't work for us, so we made a second approach, which is proof and error, and that lead us with the following q and r values. For the q in the 1 space, we got 1.9 for the x1 state, and remember that we are not considering the x2, which is the derivative of the x1. So we are gonna place these values in our script. So for q we have 1.9, for r we have, don't remember, 0.1. Okay, and the same set point and everything else. So we click play again, and we see that we have different dynamic, and as you see it is quicker than before. So, and it is the same graphs as displayed here. So for the Riccati's equation we got the same graphs. For the dynamics of the system it's the same. So let me zoom in to see what is happening accurately. Okay, we zoom in more, and let's zoom in a little more. And as we see, it's not reaching, it is closer than before, but still not reaching the 10 volts reference. So it gets stuck at 9.86, which for practical purposes we are gonna assume it is okay, since it is inside the 2% error criteria for the time response. So we are gonna work it out with these values in the following presentation. So just let me display the last two graphs. So this would be the optimal control law performance over time, and as we see, it is a pretty high value for the first voltage peak. So theoretically, in order to make this system work as shown in the graphs, we should have a voltage reference, a voltage input of at least 45 volts. So that's pretty high, and that's non-realistic for a real physics system. But still, we are gonna work with this solution, and then in conclusion, we are gonna discuss the problem and the alternative to solve this issue. And the final graph would be the cost function, and as you see, it is the same. So now we are gonna simulate this model with some op amps. So in order to make the simulation, we are using MATLAB from sorry, we are using Simulink from MATLAB, and here it is our optimal control law. So for the first state, which is the voltage, the output voltage, we are going to multiply by some constant. For the second state, which is the derivative of such voltage, we are going to also multiply its derivative by this term, and we are going to subtract some constant value. So we remember that the first state it is the voltage output, the second state it's its derivative, and for the simulation we could use some voltage controlled source and program that voltage source, and just uh, eliminate all these extra electronic components, and just leave that controlled voltage source. But I think it would be funny to make analog analogy of this equation in terms of op amps and passive components. So we are using more op amps to simulate the input optimal control law, and this would be our system or plant, and this would be in the input of our plant would be our control law. And how does it works? Let me explain. So let me go back to the presentation. So the how does it works? How do with this op-amp configuration we can get some we are gonna follow the control law. Well, remember we have a voltage reference, which is it's just taking the voltage value from the output and just to amplify that value, and then we are gonna we need to somehow derivate that same value and also multiply it with some gain, and then we are gonna subtract some constant voltage source. So the first op amp in the left is an op amp with a summing configuration, and the equation for a summing amplifier it is the following. So for the first voltage value, it is the some constant reference. So here it is just taking the reference value over the resistor value, and that and multiplying that with the output voltage, and that will give us an output voltage for the first op amp. And then for the second uh, voltage reference, we take the same voltage output voltage for our plant, but instead of having a resistor, we have a capacitor, and that a capacitor with a resistor reference gives us a configuration of a derivative op amp. And so V2 over C2, which is the current, gives us the following equation, which is the C, the capacitor value, multiplied by the derivative of the output voltage of the system. So the voltage in the op amp, in the first op amp, turns out to be the following in the following equation. So now we are gonna take this value, and we have another inverting summing amplifier, and we feed the first resistor, the first voltage reference, with the one mm, that is giving us the first op amp, and the second voltage reference comes from a constant voltage source, which is with the same value as in our control equation here. So we are gonna subtract that value, and remember that this op amp inverts its values. So here we have some negative values, so we have negative state values, and then we are gonna add positively the constant voltage reference, and then we are gonna invert that equation again, giving us some positive state space values minus a negative voltage value. So in order to these magnitudes to meet our desired ones in our control law, so we are gonna solve algebraically for those values and propose the following uh, parameters, the following magnitudes. And that is what we have in our Simulink model here. And then we are gonna simulate this model at the same final time. So it is still loading, and it should give us the following dynamic. So as we see here, the yellow one would be the our output voltage value, and the pink one would be our I think I got some error. Oh, no, it finished it. So I'm gonna open the graphs. Okay, so here are our graphs. So let me fit in the screen the performance of each value. So as I said before, the yellow one would be our output voltage system, which is the X1, and the pink one would be our input, or U, in the state space model. So if we compare these graphs with the ones in our Scilab scripts, we see that the control law dynamics is the same in the Scilab one than in the MATLAB simulation. So comparing the state dynamics, so let me zoom in again in our Scilab script. So we see, and let me zoom in also in the MATLAB graphs for the X1. And now let's compare the two graphs. So we see that it is also the same dynamic. And let's compare the steady state value. So if I'm not wrong, I can click here, and so at steady state we have a constant output value of 9.86 volts, which is the same in our Scilab script, in our Scilab scripts. So comparing those two, we get the same dynamics, 9.86 and here 9.86. So the control law proposed, the control law designed, it does work, but as we said before, it's still not reaching those 10 volts reference. So what should we do to in order to meet the 10 volts? So remember that we were not considering the H matrix. So if we do consider the H matrix in our cost function and follow the following recommendations, that the K matrix should be with the final values of H, and the same for the S matrix, but would be the minus H multiplied by the reference value at the final time. And if we solve and design our controller taking these considerations, what the controller will do is to integrate the error and modify the con- control law even though it reaches the point where it is getting stuck. So it will actually keep modifying the input till the output voltage meets the reference. So taking that in consideration, we can redesign the controller, and also what we can achieve is that the input value might might be a realistic one, because as we remember, the input value reaches non-realistic values of minus 43 volts, which is non-ideal for controlling a 10 volts reference. So actually we can set a restriction of plus minus 10 volts for the input, or plus minus 12 volts, and work it out with those restrictions. But in order to do that, we have to also take the edge restrictions. And the following steps for this project is to redesign the controller taking such restrictions, and also to make the physical system and to prove that the control law design does work. So this would be our final project for the optimal control course. It was a pretty fun subject, and thank you for our attention. Also, all the codes are in our GitHub, in some GitHub repository, we designed this repository. Is it's not taken from other repositories. So this repository we designed it. So here it is my GitHub, Andres San Martin. So all the code is legit. Okay, thank you for your time.